can bind to, that molecule there. The other part of the myosin is this ATP binding site, and that's the molecule which gives the cell energy. So the ATP can bind to give energy for the whole muscle contraction process. Yeah, no? So, I'll show you this animation again, and then I'll go through it again. So, I'm just going to go through this one.
Oh, yeah.
Yeah? So when the muscle's contracting, don't start freezing now.
No.
It'll make, so you've got your thin film and your actin, you've got your binding site on the actin for the myosin head, and that's that myosin head, yeah?
Yeah.
So when the muscle contracts, the myosin head binds at the actin binding site to the actin.
Get it? Yeah, I do.
Yeah? Okay. And then it can move the actin forward so the actin's getting closer together, the sarcomere is moving in.
Yeah.
And then it can continue to release, binds to the binding site, drags the actin closer. Binds to the binding site, drags the actin closer. Okay. I'm going to add two lots of detail now. So, first time I'm just going to go over everything I've just talked about. Second time now I'm going to bring in ATP, and that's it, I promise I'm done. Okay, let's have it go. Forget about the ATP for now. I'll bring it in the second time. Don't worry, I'm going to bring that. I'm not going to talk about that yet. Okay, so we've got our actin. We've got those binding sites on the actin for the myosin. So that's that thick filament, and that's the myosin head. It's got an actin binding site, which is probably around here, and it's got an ATP binding site, which is here. Right. So when the muscle contracts, calcium ions are released. So a nervous signal comes to the muscle, releases these calcium ions. The calcium ions bind to this troponin molecule. When they bind to that troponin molecule, that moves this tropomyosin out of the way. Yeah? So then, the myosin heads combine to their binding sites on the actin. Yeah? So that is where those cross bridges are formed. So if, I'm going to come back to it, I'll go over it a couple of times just to get it there. But when we went to that image, you've got your myosin, you've got your actin, and you've got the cross bridges. That, going a little back. That there is a cross bridge. The thick touching the thin. So that's kind of that pattern that you saw with the checkered pattern, the bridge in the middle. Okay? So we've got a cross bridge forming, and then the myosin head changes shape and pulls the actin, and that's called a power stroke. It's another word I'm going to bring in now. So as it moves that format, we've got a power stroke, and then how is it going to do the next one if it wants to move the actin further in? What's it going to do now? So what's going to happen?
Is it not going to release and then?
Yeah, it's going to release and bind again. So it's almost like oars in water. So you put your oars in the water, move the boat forward, lift them up, do it again, move the boat forward. And that's the same thing. So you've got your myosin heads bind to the actin, cross bridge, power stroke, move the actin over it, ATP, the energy is needed to release them. And then they do the same thing. Cross bridge, power stroke, ATP to release. Yeah.
Where does the calcium come from?
that comes from inside the cell, so it's called in the endoplasmic reticulum of the cell, and it's released as a response to a nervous impulse arriving at the muscle cell.
So is it basically just yourself telling it to...
Yeah. So I'm just going to let that play on its own without me talking now. So calcium ions are released when a nervous impulse arrives. Calcium binds to troponin, moves the tropomyosin out of the way. The myosin head binds to the binding site and actin, forming a cross bridge. Power stroke as it pulls the actin towards the end line, towards the centre, and then ATP binds, and ATP is needed to release the myosin head. And then it can go on and bind again, power stroke, ATP to release. Cross bridge, power stroke, ATP to release. And cross bridge, power stroke, ATP to release. And then it does that until kind of reaching the centre of the sarcomere and there's no H-zone left. Are we okay?
Yeah.
Is everybody alright? Because I'm going to amp it up another, the last kind of level I'm going to amp it up to now. Are we sure? Okay, so you'll probably notice this ADP. Please don't kill me. This is the last bit, this is the last bit. And then it's not going to get any more difficult. It's just going to be extra bits of time, but it's not any more difficult. Okay, so your ATP... One second, we're back in a sec.
Can we run away now? It's 3 o'clock.
This here
Ah, look at that.
is ATP.
Ooh.
So this is kind of a molymod building of it. So it's called adenosine triphosphate. So you've got an adenine base and a ribose sugar, so it's the same kind of molecule that makes DNA, a nucleotide. So adenosine, and it's triphosphate, and it has 3 phosphate groups. A tricycle is 3 wheels. So 1, 2, 3. So that is ATP there, and the red and purple things at the end are the phosphates. When ATP releases energy, breaking that bond, that's a high energy bond, and that's what provides energy for the reactions to occur. So I'll make it back again. So, hold on. So we've got ATP, breaking that bond, pulling a phosphate off, that's releasing energy. And it forms ADP with 2 phosphates, diphosphate, adenosine diphosphate meaning 2, and 1 molecule of inorganic phosphate, PI it's called. And that releases, on average, around 33 kilojoules per mole of energy. That number will not mean much to you at this stage. But it releases a fair bit of energy compared to anaerobic. So that kind of is a molecular representation of ATP. Breaking that bond is called hydrolysis. You add water to do that, and that releases energy. In your cells, in your mitochondria, in aerobic respiration, all that does really is add those 2 back together. So you produce more ATP. And you need glucose and oxygen to allow that process to happen. And that's a really complicated process itself, so I'm not even going to any of that.
So how much of this do we need to know, this ATP bit?
This is, I wanted to tell you that bit, but it goes to ADP and PI, so
Right.
that bit splits up, so you understand the rest
And
of
then
the
it
video.
becomes ADP.
Yeah.
Right.
So ATP to ADP and PI. So it's basically just breaking that bond and releasing energy.
And,
So-
and that's what's powering the heads moving.
That's what allows the heads to release.
Right.
So this is what I wanted to show you that for. And I'm going to just go back through this animation again. So so we've got that cross bridge there. So go back. So we've got the cross bridge. It's done the power stroke already. Then ATP binds to that ATP binding site. So it binds. Too far. No. Sorry, just going back to the other diagram. It binds there. So it binds to that ATP binding site on the myosin. And that is used to release, that's the important point, it's used to release the myosin heads. So ATP splits into ADP and PI, and that releases the heads. So that has now got ADP and PI bound to it still. So it's use the ATP, that's split up, and then that's still left bound to it while it's split. So they're separate, and I've broken it. Okay. Then it forms the next cross bridge. So when it forms the next cross bridge, the ADP and PI is still bound. And then, I'll go back, it's going too quick. So the ADP and PI are bound for the cross bridge, and they're released during the power stroke. Why do they need to be released? There's two reasons. Why not just leave them there? Yeah, so one, we need to release them so the ATP can attach to that binding site. So if I've got these stuck in my hand, I can't then have another molecule of ATP come in because that's already there. I can't carry anything else. So the one reason is they need to leave so more ATP can attach to release that head. The second thing is, if we want to make more ATP in the cell, they need to go back to the mitochondria in the cell where they can reattach and form more ADP. I lost a molybud. So, kind of they reattach in the mitochondria to form more of that ATP. So, they'll leave for two reasons. One, so ATP can attach. Two, so it can recycle them. So just kind of watching it now. So ATP binds to release, forms ADP and PI, that goes in the power stroke to form more ATP can bind. And that's it. No more. And that's the sliding filament theory.
Laura, you're saying ATP forms ADP and PI.
Yes.
What is PI?
It just means an inorganic phosphate, so that phosphate that's pulled off is just a phosphate.
Also, you have got to say PI, not P.
Yes, if you say P, that's phosphorus. It's phosphate. I want to just show you an animation before I get to do the last task. So I've got one more task for you to do, just in order. But I want to show you some nice muscle contraction videos. So this is the whole process. Cool.
You use muscles every day to do activities. This woman is using muscles to breathe, circulate blood, and move her hand to take notes. Your cardiac and smooth muscle tissues are involuntary. You do not consciously control their actions. Skeletal muscle works under voluntary control. Skeletal muscles are composed of bundles of muscle fibers. Muscle fibers are long cylindrical cells containing several nuclei. Muscles will contract or relax when they receive signals from the nervous system. A neuromuscular junction is the site of the signal exchange. This is where the synaptic bulb of an axon terminal and muscle fiber connect. Muscle fibers are composed of many myofibrils. A myofibril contains contractile units called sarcomeres. Sarcomeres run adjacent to one another down the length of the myofibril. Each sarcomere consists of alternating thick and thin protein filaments, giving skeletal muscle its striated appearance. The muscle contracts when these filaments slide past each other. The thick filaments are myosin, which are anchored at the center of the sarcomere, called the M line. The thin filaments are composed of the protein actin, which are anchored to the Z lines on the outer edges of the sarcomere. Because the actin filaments are